So I think then this is all the talk of this session. And then I invite our speaker to turn on your cameras, and then we can start, like panel discussions. Okay. So probably we could start with the answering some question. I think that's a question to Bilge. I'm not sure if Bilge is here. Are you there? Okay. Yes. So yeah, super, perfect. Okay. So I think we have all very interesting talk from, like cell oscillating gel to soft material and learning, and also from you, Vika, from this kind of, like combining the chemistry and soft robotics, and also reacting to the photo tasks, and also the last talk from Thomas on this kind of very interesting learning mechanisms. So I think what we can do now is that there's I think two questions to you, Bilga. If you can look at the chat, I'm not sure if you can see that. Maybe you can answer that first.
Now I answered.
Yeah.
I was
Okay.
typing.
I see. Okay. Super.
It sounds, if I may respond, you say it's too complicated, but to me it sounds easier than salt, but I guess that's my different background in mechanics and not being a chemist.
The chemistry of paper is very hard to control. We were so lucky to pick up the best paper that works in the first experiments. Then whatever we tried, it didn't work very well. And sometimes, yeah, the thickness of the paper is also important. So you can imagine any kind of mechanical property influences this. Yeah, but yes, the answer is yes.
Actually, I have this follow-up to this question. I'm just wondering in terms of these papers, robots, what is the repeatability in your experiments? Like how many times if we repeat this life cycles? Yeah.
Yeah, so it is very poor. So if you simply get a common paper and whatever common means, I don't know, and a hydrogel like physically cross-linked hydrogel, it's only up to 50, at most, 60, 70 cycles. But that would be, even with that number, it's a miracle. But if you have cross-linked gels and you can functionalize your paper to stick these gels on the paper, then it is, of course, a much robust material with better reversibility. If you have physically cross-linked gels, they usually shrink and they do not come back to the original size when they are dehydrated. So if you let them dehydrate completely, for example, you cannot rehydrate them. They're just dead. So there's also a range of, you can say, hydration, percent hydration where you can work. But as I mentioned, if you have more sophisticated gels, like, for example, Professor Maida's engineered gels, then you can get probably a better reproducibility and control in the hydration and dehydration.
Sounds like the plants in my house.
Yes.
Yeah.
And maybe this is also a question to Maida. So what is the repeatability if this cell oscillating gel that you show?
So you mean that the repeatability of the gels?
Yeah.
Basically, it's good because the gel is chemically cross-linked. And the problem of the gel is basically the response speed is basically very slow. So today I didn't talk about the details of the dynamics of the gels. Basically, gel shows very slow dynamics, like diffusion process of the polymer networks. So in this area, the repeatability is okay, but how we control the response speed of the gels. So this is a very big problem in the gel research area.
Okay. Yeah. So maybe oh yeah, okay, please, Bart, please.
Yeah. So I was wondering for these gels, so what is the kind of, I mean, it must be using something to go through this oscillation. So is it something you have to continuously add? You tune the environment, you add energy from the environment. What is
Okay.
making these systems continue to, I don't know, I'm not too familiar with the system, but
Okay.
what
I see. So I didn't explain the details of my research. And can I share my slide again?
Yeah, I
It's
think
okay.
you could also share. Yeah, I think you
Yeah.
are
So
shareable. Yeah.
So this is my experimental setups. So this is the gel, and then we put the gel into the chemical solutions. So basically, we have to make an open system. So gel is, it's like gel is open system. So they absorb the chemicals from environment, and then some chemical reactions is happening inside gels. And then gel produce a mechanical energy from chemical energy. So the point is we have to make open system, and then we can make a non-equilibrium systems, like she told them today.
But
So
it's never reaching equilibrium. I mean, I can imagine you go through oscillations, but it's not reaching an equilibrium.
No. This is very non-equilibrium systems. So basically, it's like heart. So they shows the limit cycle behavior. So very dynamical systems.
And what is then the energy being used? Where does the energy come from to produce this?
The energy source is from chemicals, chemical reactions.
Okay.
So we have, so this is typical.
You have to add chemicals to, okay.
Discuss the structure in the gels.
Yeah, I understand. Okay.
Yeah.
Mm-hmm. Okay, so maybe I have one general questions to all. Yeah, like just to like think about what could be like the next step. So I think what we all show today is kind of we have a system that we can like manipulate the system. One important thing to bring the system, for lifelong autonomous operation, I think that is one of, like many goals of robotics. So according to this, I want to hear some of your opinion on first thing, to make the system more resilient, that require also, of course, sensory feedback or sensing, which I think Thomas showed nicely on these tactile sensors. But in the system, like what Bas you show, or Maida or Bilka, what you show. So how we can think of, first integrating embedded sensory informations into the system for lifelong autonomous operations.
So maybe if I can respond to that. So I'm wondering whether or not we need to add dedicated sensors in these systems. So I think the fact that your soft system interacts with the environment, that is already also sensing information, because you change, there's an immediate feedback in these kind of systems. And I think if you're able to harness that, you could get to some dynamic state, to some dynamic walking gait, like you also see in animals, right? Those are dynamic states that I think also probably work without having sensing information, but there's a coupling to the environment that causes this. So I'm actually curious about these hydrogel or these chemical systems, to what could be these environmental couplings. So let's say you take two of these systems, can you make them oscillate asynchronously, or can you do that with many more? And how would you do that?
Yeah, that's a good point. Can I share again? So in the chemical systems, and so this is very important, the idea to make sensing, or so interactive system is very important. And okay, just a moment. This. Sorry, this is the tools. Okay, so when we apply some, forces to the gels, and the gel, deforms, and then the chemical reaction is coupled with the bodies of the gels. So chemical reaction is also changed by their force or volume changes, and then the system changes. So through this, I think there is some sensing. So the important thing is that how we couple the two things, body and chemical reactions. So this is most important things to make some functions like sensing or something.
So how much are you depending there on the mechanics or the deformation that is changing the chemistry? Or I can imagine that with small deformations, it might not be that sensitive, but maybe if you add some weird snapping or losing contact, I guess,
yeah,
could you introduce maybe some very sudden changes due to interactions with the environment?
Yeah, small, it's up to the situations, but there is some deformations or shape changes, change their concentrations of polymer, and then reaction is changed. So this is the, I think, kind of the sensing or some other, like sensing, I think. And actually in the simulations, in numerical simulations, we apply to these gels, for instance, and then we, push something together. Finally, the gel are synchronized together. So the coupling between chemical reaction and the body is very important.
Very nice. Thank you so much for. I think this is Bas and Maida. You stated a very interesting and important point is that. So let's say if the body can be deformed, and then we can extract those information from the deformability of the body, and that is a part of the sensings to some extent, right? And then actually this leads to my next question, which actually also I think related to what Fumi is writing on the chat message. Now, when we talk about learning, okay, so first we have some kind of, like sensing into the soft or this kind of gel system. When we talk about learning, like what Fumi mentioned, like AI and machine learning, how can we exploit those kind of mechanisms into this framework? Like, for example, what Bas has showed today or Thomas has showed today, and how we can extend those into like in your two application from Builder and Maida. Maybe any of you want to respond on this? Thomas or Bas, or yeah, please.
Yeah, I think that's an interesting question. I'm actually just writing. This is only my break for writing a proposal about exactly this, so maybe I can steal some of your thoughts as well. But I mean, I think using only the body can only bring us that far, right? We can make smart systems that have dynamic attractor states, and I think the interesting question is going to be how is that embodied intelligence? Let's call it that, or physical intelligence, however it's called. The question I think is how can we harness that in such a way that the task for the computational intelligence or the AI becomes easier, right? So I think here there's really a question between design of the body and the mechanical behavior and the task and the difficulty of learning. And I think also Thomas mentioned things in this direction, right? He mentioned basically that learning might become easier when you have a specific design or when you go soft. And I think I think we just have started to scratch the surface of understanding actually this interaction between these two seemingly separated fields so far, I would say, right? So really this interaction between how the body helps the learning could help or speed up or reduce the data required or these kind of things and make the system more robust? I think that, to me, that is an interesting question to start to tackle. But I don't know, I'm curious how you feel about that as well.
Yeah, I agree. I think the biggest challenge is getting the right data. If you have the right data, learning algorithms are all the same. And they would want. Challenge is in getting the right data and the right amount of data, and also to make sure that the system can do that task. So most of the software devices that we develop are not at the stage where it can solve a lot of general tasks. So that's purely because the hardware is not good enough. You have a hardware which can control or do the tasks that you want to do. Then the next question is how to get the right amount of data. So if I'm using a machine learning model, so they can fit some control. Maybe yeah, we still haven't reached the stage where we have good enough designs that can tackle some of the challenges that.
Nice. So actually, I think one point I want to add to this is that what we did also in our lab, one experiment, what we did here is that we have, like physical robots, like hexapod robots, and we let it learn to do some walking behaviors. We compare two things. One scenario is that just a pure hexapod robot with, like stiff body. And then we see how the learning or how the robot explore the search space. Then we compare that by adding, like adhesive material, some soft material. For example, climbing on the slope. Interestingly, we found that when we add just additional, like physical intelligence or the proper material to the system, it's scope or it's somehow it guide the learning strategy such that instead of, the system need to explore a lot because it has also some constraint from the body that interact with the environment. By this kind of interaction, it's also constrain a possibility of search space. And that is a kind of, like in the way it also it guide the learning strategy in the sense. Yeah. I think maybe Thomas, you have seen that maybe in your this type grasping experiment, right?
Yeah, exactly. And I think it's a bit surprising. Yeah. We don't really know why it is, but things seem easier when you're working with a soft system.
I think in the systems I showed, one of the first with these very basic robots, I also observed something similar. So there you can tune the softness of the connection of the actuators, and you go from basically full control, no effect of the environment, to very soft, right? And what we see there is that the softness actually smoothens the environment, which makes it in a way easier to get, I won't say the system gets gradient information, but it becomes easier. It becomes more sensitive to that kind of information, and it is able to easier step towards that environment. So I think adding that softness will actually also make this maybe the system even more predictable. I guess that's a similar point again as Thomas, but I also observed that in the systems we studied as well, although we didn't. Now that you say this, right, I didn't necessarily we dove into understanding this, but this is at least an observation we made.
Yes. I think this is a really, really nice conclusion. And also what we observe is that softness also reduce the gradients to some extent, like the errors. For example, when you have rigid material or rigid objects, and then you have a robot arm bump to the objects, and you get a high peak of the errors because of the high impact. But when you add the softness, that the error information become decreased because of the softness that reduce that error. By doing that, it also can reduce the learning process. Either way, yeah. So I think that's this kind of like what we can conclude and wrap up on this. Maida and Bilka, if you have something to add on this learning aspect into your system, or you may have some thought on that. Do you have any?
So you mean that how we make a learning process in chemical systems, you mean? So one, it's
Yes.
like in the physics, there is some like there is reservoir computing. in the AI system. And in physics, they showed some reservoir computing using nonlinear coupled nonlinear oscillators. So one thing is that we make so many oscillating gels and then make some interaction together, and then we may make some like computational gels using so many interactions of the gels. So point is how we make interactive systems among gels or nonlinear oscillators. So is this okay?
Yes, yes, yes. I think you hit also a very interesting point on the reservoir computing, where that is a kind of embedded temporal memory into the process.
Yeah, yeah.
Yeah, right. Yeah. That's nice. Bill, maybe you have something to add. Yes.
I was thinking about what Bas just said. Yes, the body can contribute largely to the output, the motion output. We have already had a system, a walking robot with soft and hard components with the same geometry, and they were behaving much differently. And I'm thinking that if we can incorporate even a chemical metabolism, then it may also add another feature, and that can also affect the outcome and the intelligent behavior of the robot in the end. So there are several ways that one can go with the material itself, the material surface, the inner chemical metabolism. This is what I call in the gel, and the geometry itself is another factor. So many different parameters can be used. Usually, I don't want to be I don't want to make a negative comment, but usually when we draw the computational models, we do not get into the mechanical properties. We just model the shape of the things, but it's more than a shape when we manufacture them. So there are different features inside, and they should be used. That's what I want to say.
Excellent, excellent. That's nice. I think we have maybe like last 2 minutes. So maybe I put one more aspect in the panel discussion here. So right now we discussed already on sensing part, on learning part by using exploiting the body deformabilities and like nonlinear dynamic system. One thing which I think maybe we can think about is that predictability. Predictability means that let's say we have a system at here. In terms of soft robotics, the system need to be there in order to send informations if we need to detect the deformability of the body. But in natures, we have variety of sensor modalities, visions, smell, that we can obtain those information in advance. The next aspect is that storing those information and recycle that later in terms of like memory aspects. Like for example, I always use this example as a cat, which we done one experiment in the past is that when we look at the cat can step over the obstacle from the front leg, and the hind leg step over the obstacle without hitting it. And in that regard, there is no sensory information activate for the hind leg movement, but the cat amazingly store those information through some kind of neural memories and recycle that in the right time. So I think that could be something we can like thinking in terms of implementing this in the soft robotics. Yeah, that is my last comment. Yes.
Okay, thank you very much, Paramit. I think this was a really amazing end of the conference with actually the right topic in the heart of embodied intelligence, right? Talking about how to actually make any embodied system doing anything intelligent computation and adaptive behaviors. And all of you have actually nicely interpret all the different approaches, based on chemicals, based on machine learning, based on mechanical structure, soft bodies, and then including, the crazy materials like papers. And I think that was a wonderful illustrations of how embodied intelligence can go beyond our conventional imagination. So thank you very much all for the wonderful contributions for the last session, and then a very interesting discussion. So I'd like to appreciate your contribution here. We can continue these discussions after the final remarks of this conference. So Pramit, well done. Thank you very much for the mediating all the interesting discussions.
Thank you so much.